Let's jump right in. Welcome to this informative session. Today, we are diving into what is honestly the ultimate detective story in the history of chemistry. For centuries, people have looked at the world around us, the water we drink, the air we breathe, the ground we walk on, and just wondered, what is this actually made of? Well, today, we're going to unpack the incredible scientific journey that finally answered that exact question. We're looking deep into the structure of the atom.
So I want you to try something. Just imagine, for a second, shrinking down, like shrinking down millions of times smaller than a single grain of sand. If you could do that, you'd finally be face to face with the literal building blocks of matter. Now, we've all been told that everything is made of atoms, right? But that honestly just leads us to a much more fascinating question. If everything around us is made of atoms, what exactly is the atom made of?
Okay, let's dive into this. The answer definitely didn't come all at once. It took this rapid-fire sequence of brilliant minds over just a few decades to really crack the atomic code. Think about it. In 1886, Goldstein discovers positively charged protons. Then boom, by 1897, J.J. Thomson finds the negative electrons. Cut to 1911, Rutherford uncovers the nucleus. Bohr maps out electron orbits in 1913. And finally, Chadwick finds the neutron in 1932. It was like a scientific relay race. Each of these scientists built on, and honestly sometimes completely debunked, the guy who came before them.
Now, to really appreciate how wild this timeline was, we got to look at what people used to believe. The word atom itself comes from the ancient Greek word atomos, which literally means indivisible. For thousands of years, we're talking all the way back to the Greek philosopher Democritus and later John Dalton in the 19th century, that atom was the end of the line. People thought it was just this solid, locked, unbreakable sphere. Literally nothing could be smaller.
But that whole indivisible illusion, it completely shattered in the late 1800s. See, when Goldstein discovered positive canal rays and then Thomson found negative cathode rays, the scientific community had this massive realization. The atom actually had inside parts. This led Thomson to propose the very first subatomic model. It's affectionately known as the plum pudding model. He basically said the atom was a solid sphere of positive charge, with these tiny negative electrons just stuck inside it, kind of like raisins in a dessert pudding. It was a neat, comforting idea. But spoiler alert, it was totally wrong.
Enter Ernest Rutherford in 1911. He decides he's going to test this plum pudding idea. He takes an incredibly thin sheet of gold foil. We're talking just 0.00004 centimeters thick, and he blasts it with highly energetic alpha particles. Basically, he's firing tiny, positively charged subatomic bullets. Now, if the atom was really just a soft pudding of positive charge, those heavy bullets should have just punched right through, no problem. And, well, most of them did. But then came a massive plot twist. A few of those particles deflected at these crazy huge angles. And a very small number, they bounced completely backward.
And this brilliantly illustrates why that one unexpected bounce literally changed everything. Rutherford realized that because almost all of the particles went straight through, the atom's volume has to be mostly, well, just empty space. It's absolutely not a solid sphere. Plus, those few particles that ricocheted backwards, that proved that all the positive charge, and pretty much all the mass, was packed into this incredibly tiny, super dense center. He called it the nucleus. The negative electrons, he figured, must just be orbiting around that tiny nucleus out in all that vast empty space. Now, Rutherford's model was a huge leap forward, but it had a fatal flaw. And it's a really big one. You see, according to the strict laws of classical physics, a charged particle orbiting around a center should be continuously emitting energy. If electrons were constantly losing energy as they zipped around, they'd inevitably lose momentum and just spiral right into the nucleus. The atom would instantly collapse. So if Rutherford was 100% right about how this worked, matter just shouldn't exist. You, me, the planet, we'd all literally collapse in on ourselves.
And this is exactly where Niels Bohr steps in to quite literally save the universe in 1913. He took Rutherford's model and merged it with Max Planck's brand new quantum theory. Bohr proposed that electrons don't just orbit wherever they want. Instead, they live in very specific fixed energy orbits. And here's the kicker. As long as an electron stays in its designated orbit, it doesn't emit any energy at all. It's exactly like standing on a staircase. You can stand on the first step or the second step, but you can't just hover in the empty air between them. By introducing these quantized energy levels, Bohr finally explained why atoms are actually stable. And that idea of quantized energy leads us directly into what we call electronic configuration, which is really just the way electrons are distributed around the nucleus. They're arranged in these different shells, labeled K, L, M, and N. and even smaller subshells like S, P, D, and F. The thing you gotta remember about electrons is that they're kind of lazy. They always want to be in the lowest possible energy state. So, they fill up the shells closest to the nucleus first before they move outward. This whole structured arrangement isn't just random science bookkeeping. It's literally the ultimate quest for atomic stability. But here's the catch. These shells have very strict capacity limits. The first one, the K shell, can only hold 2 electrons, max. The L shell holds 8, and the M shell holds 18. And it's this rigid, non-negotiable capacity that dictates the chemical reactivity of literally every single element in the universe. Take sodium, for example. It has 1 extra lonely electron in its outermost shell. Meanwhile, chlorine is missing exactly 1 electron to complete its perfect shell of 8. This mutual desperation for stability is exactly why they react so aggressively to form the regular table salt you put on your fries. But wait, even with Bohr's perfect orbits, the math just wasn't mathing. The total mass of the atom didn't add up if it was just protons and electrons. Rutherford had actually predicted back in 1920 that there had to be something else hiding in that nucleus. But it wasn't until 1932 that James Chadwick found the final piece of the puzzle. By shooting alpha particles at beryllium, he uncovered a brand new type of highly penetrating radiation. These new particles had the exact same mass as a proton, but absolutely zero electrical charge. Boom, he had discovered the neutron. And with Chadwick's discovery, the anatomical structure of the modern atom was finally complete. Think of it like a subatomic roster. We've got the electron, carrying a negative charge, basically weightless, just zipping around in those specific outer shells. Then, locked deep inside that super-dense nucleus, we have the proton, rocking a positive charge and a mass of 1 atomic mass unit. And right alongside it sits the neutron, perfectly neutral, but carrying that exact same heavy mass as the proton.
Now, what's really fascinating about this is a brilliant little twist in nature. We used to assume that every single atom of a specific element was an exact, identical twin. But they aren't. Enter the isotope. Isotopes are atoms of the exact same element, meaning they have the exact same number of protons and electrons. Because of that, they act totally identically in chemical reactions, but they have a different mass number. Why? Because nature sometimes decides to pack a different number of those neutral neutrons into the nucleus. Let's actually look at this in action with the simplest element out there, hydrogen. Natural hydrogen actually comes in 3 different variations. First up is protium, which makes up almost all the hydrogen in the universe, and it's totally unique because it operates with absolutely 0 neutrons, literally just 1 proton and 1 electron. But then we have deuterium, which sneaks exactly 1 neutron into the nucleus, instantly doubling its mass. And finally, tritium, which packs in 2 neutrons. They are all still hydrogen, but they just weigh slightly different amounts.
Now, I know counting neutrons might just seem like microscopic bookkeeping, but tweaking that number inside a nucleus, that can unlock massive, literally world-altering potential. And honestly, no number represents that raw power better than 235. Let's talk about uranium. In nature, almost 99% of it is the isotope uranium-238. It's a heavy rock, and it's relatively stable. However, a tiny, tiny fraction of natural uranium is the isotope uranium-235. It has just 3 fewer neutrons in its nucleus. That's it. But that tiny subatomic variation, just missing 3 microscopic neutrally charged particles, makes uranium-235 unstable enough that it can be split apart in a chain reaction called fission. That one specific, rare isotope is the entire reason we can power massive nuclear reactors and light up whole cities. It is just incredible to think about the journey we've been on. We went from assuming matter was just these unbreakable solid spheres to realizing it's this intensely dynamic system of quantized energy and tiny particles. Literally everything we are, everything we touch, the massive power grids we rely on, it is all built on unbelievably tiny nuclei surrounded by vast empty space. Which leaves us with one final, kind of mind-blowing question to think about. If the atom itself is almost entirely empty space, what other infinite untapped energies are still hiding right there in the microscopic voids of our universe? Thank you so much for exploring this with me today. Keep asking questions and keep exploring.